Previous lesson we've been talking about matrix multiplication, basically the properties of matrices. In geometry, this is really just sort of an introduction to matrices. You'll get a lot more of this sort of in Algebra 2 or in a pre-calc or beyond class, maybe a college algebra class. But for now, we're really just looking at some of the basics of matrix multiplication. And the idea here is really to recognize, can you first identify the dimensions? So for instance, this is a 1 by 3 matrix. This is a 3 by 1 matrix. Can you multiply those together? Yes, you can, because the inside terms, the 3 and the 3, are definitely the same. So that means you're going to produce a 1 by 1 matrix in the end. I'll reveal this hopefully kind of quickly here. And as you can see by the work, we multiply, we go across this way, we go down this way. So we say -3 times -5 plus 2 times 0 plus 6 times -3, just showing the work there. We simplify one step, we add this together, we do get a 1 by 1 matrix in the end. So the outside dimensions give us the width and the length, I guess, of our other matrix. Here we have a 2 by 3 matrix and we have a 3 by 1 matrix. So it means our resulting matrix should have 2 rows and 1 column. And when I reveal this, I'll just reveal this all the way here. Sure enough, we do have a 2 by 1 matrix down here, and that looks pretty good. So we take 0 times -4, 3 times 2, 5 times 7. We add those together, we get 41. We take 1 times -4, 0 times 2, and 9 times 7. That should give us 59. Lastly, we have a 2 by 2 times a 2 by 2. This is a square matrix times a square matrix. Will result in the same square matrices. These are a little bit more complicated because it's hard to keep track of what's going on. What we do is we take the first row times the first column, and that should produce the first row, first column number, which is 38. We'll take the first row times the second column. That would produce this business here, which produces -50. We take the second row by the first column. That gives us our second row, first column numbers, which make this element down here the -23. And finally, second row by second column produces this, which gives us -43. Again, we write this as a 2 by 2 matrix. So a square matrix times a square matrix gives us back the same square matrix, provided they all have the same dimensions. And if you need more on this, there is another video, just my previous video, talking more about matrix multiplication. Let's talk more about the application. It says use a description of a translation of a triangle to find the value of each variable. So what you have to do is you have to recognize that one of these is going to be a translation matrix and one of these is going to be representing the coordinates of the triangle. So with the translation matrix, which is going to be this first one, all the coordinates representing the x are going to be the same. So I would imagine that x is going to equal -8. The idea here is that we're going to shift all these x coordinates the same amount, -8. It means all the y coordinates are going to be shifted, that's these down here, will be shifted the same amount, 4, 4, and well, y is going to have to equal 4. From there, what we're going to do is we're going to set up some sort of, that gives us 2 answers. In order to find these other ones that are in here, we'll just simply say -8, that's not an 8, -8 plus -2 has to equal r then has to equal -10. We're just taking the first element plus the second element has to equal kind of the first element, first element, first element. We continue that, we would say x, which is -8, plus b has to equal -4. We add 8 to both sides and b should equal 4. In a similar manner, we could say that for d, we could say 4 plus d equals 7, d equals 3. We could say 4 minus s equals 5. I'm sorry, 4 minus 5 equals s. 4 minus 5 equals s, so s equals -1. Let's see what variable I missing. I have c probably. Where's c at? C's up here, so we'll say -8 plus c has to equal -3. If I add 8 to both sides, c has to equal 5. Okay, so that's one way to find all these numbers, all these variables. And I think the key comes in where we have to talk about if this is a translation of a triangle. One of these has to be the translation matrix, and one of these has to be the actual matrix representing the coordinates. So it says what are the coordinates of the vertices of the image? Well, that would be This would be one coordinate, say like negative 10, 7. Another coordinate, say B might be negative 4, negative 1. And maybe the third coordinate could be negative 3, 6. Those could be the new coordinates. Maybe they have primes with them as well. I'm not exactly sure. This is kind of an ambiguous problem, but the idea here is that you can solve this using matrix addition. They could make this a little bit more complicated if there was matrix multiplication. Obviously, these dimensions wouldn't work. But the idea is they could give you maybe a square matrix, and like another square matrix. They could end up multiplying these. You could probably set up some sort of system of equations in order to solve this. Okay, more application. It says 2 offices submit supply lists. A weekly planner costs $8, a chair mat costs $90, and a desk tray costs $5. Use matrix multiplication to find the total cost of supplies for each office. So it does say matrix multiplication, and it does say for each office. So at the end, I will have office 1 as an answer and office 2 as an answer. So we'll see how this turns out. Obviously, I have something here. I can set up this matrix, just writing down kind of what their supply orders were. And what I like to do is I like to look at this and say, well, this is definitely a 3 by 1 matrix. What other information am I given? Well, I'm given a cost here, and a cost here. I'm giving 3 costs. So the idea is I either have to multiply this thing by a something by 3 matrix or a 1 by something matrix. Since I have 3 of something, I'm probably going to multiply this by a 1 by 3. So what I'll do is I'll break this into the costs. That'd be 8, 90, and 5. Maybe I should leave more space in here so you could tell the difference. When I multiply this out, I would simply take 8 times 15 plus, let's see, how am I going to write this? This is going to be a, in the end it'll be a 1 by 1. That's not right. This is definitely a 3 by 2. So I'll have a 1 by 2 matrix. So 8 times 15 plus 90 times 5 plus 5 times 20, and that would give me the office 1 total. I'll leave a little bit of space here. We'll have 8 times 25 plus 90 times 6 plus 5 times 30. When I simplify this, I need another parenthesis on there. I should have, I think it's okay to write the dollar sign here. So 670 and 890 would be the totals for Office 1 and Office 2. Sort of an extension on this, instead of having just Office 1 and Office 2, maybe these are Client 1, Client 2, Client 3. And if you imagine this being like on Amazon as opposed to just this office supply company, Amazon has like thousands and thousands of orders, and then if it kept track of every single thing that it sold sort of in a matrix, instead of just being a 1 by 3, it'd be like a 1 by a million. And then each person and their orders might, look differently. They'll order 0 of these, 0 of these, 0 of these, but 26 of those, 19 of those, 7 of those. And that would make some sort of matrix for every single order. Maybe this would be a better example with something besides Amazon, which is that big. But the idea here is this is one way that computer scientists can actually build buying software is based on drop-down menus that someone's purchasing this, what's their quantity, and they can actually put it into a matrix really easily and have the computer itself calculate these answers. The school play. School play was performed on 3 evenings. The attendance on each evening is shown in the table. Adult tickets cost $5. Student tickets cost $3.50. First thing says use the matrix addition to find the total number of people that attended each night of the play. That tells me that I'm just going to break these into nights like this, and we'll say 425. I'm sorry, by adults and by this. And we're going to add this to 250, 360, and 390. In the end, when I add these together, I get that 590 total people were there the first night. Second night, I just sort of add these across. I would have 785. And the third night, I simply have 830 total people. So that's how I would do this, and this would be my resulting matrix, and that's by matrix addition. It does give you a hint there. Next one says by matrix multiplication, use it to find how much money was collected from all the tickets each night. So what I do again is I'll set up a matrix here. This is the 340, 425, it's not a very good 40, 440, 250, 360, 390. we'll set this up. This is a 3 by 2 matrix. So the idea here is that if I have costs, I only have two costs really. I have this $5 for students, or for adults, and $3.50 for the students. So if I'm going to set this up, I'm going to have to multiply by a 2 by something matrix. Since I only have one thing is cost, we'll just set this up as a $5 and $3.50 matrix. So I have a 3 by 2 times a 2 by 1. I should get a 3 by 1 matrix as my result. So that'll look something like this. When we multiply these out, it just really makes sense to me that we're taking 340, which is the number of adults, times $5 plus, we'll say, $2.50 times $3.50. And that really makes sense for how much money they would make that first night. This is $425 times 5 plus $360 times $3.50, something like this, and $440 times 5 plus $390 times 3.5. Pretty straightforward. And again, this equals, we'll total this up. We'll get some dollar sign action on here. This would be $25.75. The second night, whoa, it moved on me, would give me $33.85. And the third night, $35.65. Okay, now you might not think this is the most useful thing, but what we're working with, again, this is an introduction to matrices, so they will get more complicated. I think the story problem's added a little bit of usefulness with it, and I think this is something that we could definitely derive, thinking, okay, well, we're just going to take this number of adults times $5, that makes sense, and $2.50, yeah, that's times $3.50, that makes sense. Then we would get this arithmetic, but the way that we get it is driven from these matrices, and I think that's the important thing, is to understand why we're doing what we're doing, how we're getting what we're getting. And I think that's the important part.